Hello, everyone. Welcome to episode 12 of the Learn System Design podcast with your host, me, Ben Kitchell. Right off the bat, I want to take a moment to thank everyone for their patience in between episodes here. Of course, we are, at the holidays, which can make, episode timing a bit hectic. But also, I spent the last week in the hospital with my sister, who was battling pneumonia and a pulmonary embolism. I am happy to share that she is in good spirits and she's on her road to recovery and she is now out of the hospital. So with all that out of the way, I am back and I want to let you know this episode, we were supposed to be focusing on drawing diagrams and that sort of design step of the interview process. And instead, this episode, we will be just jumping straight into it. We're going to jump into a practical example with every step, including the steps over the previous episodes, and then also talking about the design and the diagrams portions as well. Why do this? Well, for one, you guys have been patient and I appreciate it, but also I just feel speaking on everything together will give better context to this final section and help give you a better grasp on where everything fits in and how the whole process from A to Z actually looks. With that being said, today is the day I'm sure a lot of you have been waiting for. We're going to look at practical examples on going through designing a system. We will use everything we have learned along the way to build different types of systems. And specifically, today's episode was voted on by our Patreon members, and we will be designing a web crawler. If you've listened to the last few episodes, you will remember me bringing up these words constantly. But it is time for our ever important first step of defining our functional requirements. In case you forgot, that basically means defining what are the things our system needs to accomplish. If you are new to what a web crawler is, it simply crawls or scours or ventures across the internet with certain URLs and extracts important information. It then stores the data it gets from those pages and allows a user to search that data that's been found across the internet. While search engines like Google, Bing, or DuckDuckGo aren't technically web crawlers, they do rely on web crawlers to help them index the entirety of the internet. So what are our functional requirements? And furthermore, what are the things that could be a part of the system but might be out of scope for today's project? Well, the first one's probably obvious. We want the web crawler to crawl, right? You see, web crawlers themselves should be automatic. They will start off with a list of URLs, but they need to parse new links from those URLs to visit new pages, right? If I give it like google.com, right? Google's going to have a bunch of different links. Our web crawler needs to be able to take the links from Google that is on that page and then visit each one of those links specifically, get the data from them, find URLs in those, and, continue on doing this whole process of finding URLs, visiting the page, taking the data, finding URLs in that data, and so on and so forth. Let's take an example, right? If I wanted to set up a web crawler to find the best price for a new graphics card, I might put in a few seed URLs like Best Buy, Newegg, and maybe even Google. For the first two, we could write a script that searches for GPUs, grabs the information, and then returns it to a database, and then I can query that database and look at, Best Buy has this card for this price, that card for that price. Newegg has the same thing for cheaper or more expensive. But again, what about the Google example? Google doesn't sell graphics cards. Instead, it might have some useful links to other websites that have a better price. So therein lies our first functional requirement. We need a way for our system to queue up seed URLs as it parses new links. Even when it goes to Best Buy, clicking on the item is still a new URL. It still has to visit that page, parse that information, and save the relevant information from there. The next functional requirement we've sort of already hinted at, but we need a way for the user to fetch the relevant data, to search it whenever we've got all this tons of data about GPUs and their prices. But if we don't have a good way of actually laying out that data or fetching that data, then it's kind of useless, right? We could also add more things depending on the ask at the interview, or if this product spec wants more, verbosity. These extras might include something like a schedule for crawling specific pages, such as crawling a social media, which changes frequently, versus crawling something more static like a blog that doesn't have a lot of changes during the day. Another good idea might be implementing duplication checks. This can be, helpful for us when we're like indexing a single page multiple times. I don't really want that information stored and me paying for that storage, mind you, for the same page, hundreds of thousands of times. Finally, we could also consider page prioritization, right? Where like the most popular pages show up, if they show up more times than others, or how old the link is, or how accurate the search is. If I'm searching for GPUs, maybe I don't want to see CPU data, things like that. For now, though, let's just talk about our basic functional requirements. One being the crawler should accept that list of URLs at the start. The next is the crawler should enqueue new URLs it comes across. And finally, the last would be the user should be able to query the data parsed from the web crawler. As mentioned before, you're designing an MVP or you're working on an interview. We only need 2 to 3 functional requirements for that. If we need more in the future, that's something to tackle at another time. Don't overwhelm or bog yourself down with a lot of functional requirements that aren't needed. And the same rule of thumb applies to our non-functional requirements. If you recall from episode number 8 of this exact podcast, there's an easy pool to choose from when it comes for non-functional requirements. The complexity comes in when deciding which of these are the most important for your system. And if you don't remember this pool, I'll recap. It's just a high level, though. If you don't remember it fully, I recommend going back and listening to that episode. But the rough pool is your CAP theorem, environment constraints, scalability, latency, durability, security, fault tolerance, and compliance. The big 3 from this list, in my opinion, is scalability, availability, which is part of the CAP theorem, right? And fault tolerance. Others you might consider are like security, because you'll be crawling unknown URLs and you'll be doing it autonomously. So you want to make sure that the data you're storing is secure. Another one to consider is your compliance. If you're scanning data that could have potential personal identifying information, or PII, it is important to obfuscate this data and not expose it to individuals that shouldn't be seeing other people's personal identifying information. For now, though, again, we'll stick with our 2 to 3 of the system should be highly scalable, the system should be highly available, and finally, the system should be fault tolerant. When it comes to estimations and back of the napkin math, I've talked in previous episodes about my general disdain for capacity estimates. I want to make it clear before I jump into this that it's not always necessary. It's up to you and the interviewer or your product leader to help you decide how in depth you really want to drill down into this. In the end, regardless of calculations, you're going to end with a giant number of users, a giant number of data, and surprise, a giant number for your cost. But in reality, 99.99% of people listening to this will not need to design systems with petabytes of data and billions of users. However, I would be doing you all a disservice if I did not address this section. So let's dive into some raw numbers and estimates, because the nature of web crawling can grow exponentially. We can assume that the number of pages we will be saving is probably going to be huge. And if you remember my advice from previous episodes about how to deal with large numbers, instead of saying something like 986 million pages to sound smart and more accurate, we can instead just say it'll be roughly 1 billion. 1 billion a month. And why 1 billion versus 986 million? Because getting your queries per second threshold is a lot easier to divide 1 by 30 by 24 by 3600 rather than 986 divided by 30 divided by 24 divided by 3600, right? Like, yes, the 986 might be more accurate, but you're not going to get exactly 986 million every month. That number can change, it can get bigger, it can get smaller, and you will never have the exact number. So giving a number that makes it harder for you to do this sort of back of napkin math is just, it's going to hurt you more than help. So doing that quick calculation for you, we end up with somewhere around 390. So again, let's round that. Let's say 400 queries per second. But here's a little secret. Because we've done that math now, we don't have to do it again in the future. What do I mean by that? Well, when you're doing any calculations in the future, now you know that 1 billion of anything, doesn't matter what it is, 1 billion of anything a month is the equivalent to 400 of that same thing per second. Doesn't matter what it is. You can go into an interview or product discussion and not have to write all this out now. You can just say, well, I know that 1 billion requests a month means 400 requests a second. Taking this a step further, we can also apply to smaller amounts now, right? So 100 million is a tenth of a billion, right? Well, then what's 1/10 each second, right? Therefore, 100 million of anything is just 40 of anything a second. And of course, 10 million will equate to 4 a second. You see, like, once you sort of get this logic and you remember this math, you can just apply it without having to spend extra time working on these minute calculations. 400 a second means 1 billion a month. 40 a second means 100 million a month. 4 a second means 10 million a month. And probably goes without saying, but 1 a second is roughly 2.5 million a month. So let's talk about the other side of the coin, right? Let's talk about the data size and your storage estimates. We know we have roughly 1 billion URLs a month. So what is the rough size of any of these web pages? You can just choose a reasonable number or look it up if it's easier. But for the sake of this discussion, we're just going to say it's 500 kilobytes. Since we know that 500 times 1 billion is just 500 billion, we can consult the power of thousands charts that we talked about in our previous episodes. 1 billion bytes is a terabyte, so 500 billion bytes is just 500 terabytes. So we have 500 terabytes worth of URLs a month. Or we have 6,000 terabytes a year, which is roughly the equivalent of 6 petabytes. 6 petabytes worth of URLs that we are storing a year. From here, it's pretty easy math. How long do we want to store the data for? Conventional wisdom says 5 years, but maybe we want to store it for 3 or 7. It's as simple as multiplying 6 times 3 or 6 times 5. So roughly, we'll have somewhere between 18 to 30 petabytes worth of data at any given time. And so to summarize this, remember what I said before. Capacity estimates don't bring a lot of conversation, besides knowing that we have a lot of data and a lot of requests. But none of it actually changes or informs how we design our system. if the number is going to be huge. If the number ends up being in the thousands, sure, that might say, hey, we can cut back on a lot of these things to have a smaller, more uniform design. But most of the time when you're in these interviews, they're looking to see if you can scale to the level of billions and petabytes and terabytes worth of data. And so getting those numbers extracted just means that you know how to do basic math and you can, add, subtract, divide, and multiply, which is not very helpful for, actually designing the system as a whole. Next, we'll talk about the database models. And luckily for us, the database models for this particular design are pretty straightforward. But let's look at our functional requirements and break them down. The crawler should accept a list of URLs. These URLs are enqueued, and then the data that we get should be searchable. For the first two, we simply need a data model that has a string property with that's called a URL, and to help ensure we're not bombarding these websites with requests, we can have like a timestamp of, last visit timestamp. This will allow us to check that if it's been less than a certain time frame, less than a second, less than a minute, that we don't visit the URL again. Finally, we would need an S3 URL. And all this S3 URL is just a URL that points to a bucket in S3 where the majority of our HTML parsed data lives. We could also have some extras for metadata, like when was it created? How many times did we come across this URL? The world's your oyster. You can add as much as you want, but for this exercise, let's just stick with our URL, last visit timestamp in our S3 URL. And for that final functional requirement, the user should be able to query that parse data. Much like every part of this that we've covered before in this episode, in other episodes, from the beginning I've been saying this, that there's multiple ways of tackling this, right? I would argue that this is one of the most important decisions that we can take here, and that's how we store the data and make it efficient to search. If we were dealing with a small number of pages, like in the tens of thousands, we could get away with just parsing the data and keeping it in the database and then doing like a fuzzy search, right? If we had millions of pages, we might be able to get away with storing it in something like Cassandra and just keep our indexes clean and, really focus on that level of storing. But as you remember from just a moment ago, we have billions of pages. And as you probably remember from just a second ago when I said S3 URL, you probably are getting where I'm going with this is when we have billions worth of pages or data of any kind, we should instead just try and keep our costs a bit lower and store it in something like a large object storage, something like AWS's S3 or Azure's blob storage. Although this might be a bit more costly than running our own servers and keeping everything within our own domain here, it's going to be more of a pain in the neck. It's going to require more engineers, more people keeping an eye on the data, having backups of all of these things. Whereas something like S3 and Azure, their blob storage, will help hold all these things, have the backups, have the redundancy, and not have to worry about, the power going out at your server farm and then no one can actually access the data. That's a part of our availability non-functional requirement, just right off the bat. As far as the API design goes, the application will have two folds of communication, externally to the user and then internally for other applications, like if a search engine, for instance, wanted to use our web crawler. Depending on the situation, it can do either one or both at the same time. For the user-facing portion, we will need a way for the client to talk with the application, and a pretty quick and easy way to do this, of course, is using an API. In this case, a REST API will be more than enough. For the internal communication, we could use a REST API, or we could use something more conventional like an RPC, but for this use case, let's just use a REST API across the board. To satisfy our first functional requirement of allowing a client to pass in some seed URLs, we would have something like a post request to /v1/seed with a JSON body that has like an array of URLs that we would begin to work off of. For our next functional requirement of enqueuing new URLs as we come across them, there's nothing really we can do with the API for that, right? That's all internal communication. So, again, we could have like an internal API call that calls from one service to another service to just add those things to the queue. But we don't really have to lay that out in our API design. For the third functional requirement, we will have a GET request structure that calls /v1/search, and that will accept query parameters that will be the keywords that we want to search the data for. And at this point, what I like to do is just take a second to talk about how the data will flow through our system. Because in the next steps, we're going to be drawing the diagrams and applying this. And don't worry, since this is an audio experience, I will be including rough sketches of diagrams and doing callouts for the next portion, I promise. You can actually find a link to that below in the show notes. For now, though, let's focus on the data flow. The initial step is taking the URLs from the initial seed request, putting those into our queue. From here, the queue will make the request to the URL server to get all the initial HTML for that web page. We'll then store this data in an S3 bucket, store the URL in our database, that S3 URL property, if you remember, and of course, update our last visit timestamp in our database. Next, we'll send that raw data along to maybe a URL parsing service that will look for new URLs, and then it can just put those back into the queue. Not too bad, right? I've only introduced 2 new services that should make a lot of sense. An HTML parser and a URL parser. One parses the HTML for the data, one parses the data for any new URLs. On the other side is our external user flow for searching. A user will send a GET request with certain keywords and things they're looking for to find extra data on. The user sends a query parameter with a number of keywords, and here we find ourselves in an important situation once again. You may be already asking yourself, well, how do we search for specific keywords if the data is stored in S3? And there are, again, as I say all the time, many solutions to this. The most obvious solution is you can add a new entity in your database model, right? You can go back and you can modify that model. You have not, started designing your system. You're just planning, so it's totally okay to go back and add things that maybe you didn't think about before. This could be a nice place for Cassandra, since there will be so many rows of data where you have just a key value pair where the SD URLs are associated with certain keywords. For instance, a keyword for shoes might have a value with the S3 URLs that contain Nike, Adidas, etc. And when someone queries, shoes, they would get the data back from these different sites that have been parsed. Another solution, though, would be foregoing this entirely and using a tool like Amazon Athena or Google's BigQuery. This allows you to search your bucket's contents for that specific information. These types of queries can be more costly, but they can also save you development time. So it's important to remember to bring up the discussion here and explain why you would choose doing one of these things over the other. I might implement the database with Cassandra to save on cost, but I might implement Amazon Athena or Google's BigQuery to save on time. And it's important to just know why you're doing something and make a call out to say that. Let's now jump into the design step. This is what most people think of when they think of a system design interview. It's also the thing that most people rush to, and then they find themselves building the road while they're driving the car, right? In the show notes of this episode, you will see links to pictures with dictation, and each of these steps I'll be going through. I will call out specific sections as I walk through the process, and feel free to save these images as needed. We've already been through the first few steps so far. And along the way, we should be documenting our findings. You can see that in our first image where we have laid out our current state, showing our functional requirements, non-functional requirements, capacity estimates, DB models, and of course, our API design. And your first action in your design step will actually be very familiar to if you were writing an algorithm for the first time. You want to get the minimum viable working design. So you want to start off very basic and then build up accordingly. Don't worry about scaling or anything else except the bare minimum of completing your functional requirements. The reason we do this is because we want to show that we can design a system for just 1,000 users, but we can also scale that design up responsibly and easily if our user base grows. And as you can see, in my basic design in images 2 through 5, I've taken the time to highlight how each part of my system works with each part of my functional requirement. Next, you want to begin building out your system to work with your non-functional requirements. In images 6 and 7, you can see how I chose to scale the system, how I choose to implement strong availability. Some of the things I didn't show, but that should be touched on when you talk about these things, is how splitting that one backend service into multiple service helps us scale horizontally. Scaling horizontally helps us have higher availability. It helps us with fault tolerance. If one of our services breaks, there's plenty of others that can take its place. Try to pay attention to the changes from one of the images to the other, and always feel free to reach out to me if something doesn't make sense. I'm always here. Drop me a line on Discord, email, wherever is easiest for you. The important thing is to see how the design phase evolves. Your system doesn't need to look exactly like my system. It just needs to evolve in the same way. There are many routes that we could have touched on past this point. If you're interviewing for a higher level position, you'll be expected to identify these things on your own. You want to make callouts before the interviewer actually asks you or tries to help you give them. Don't cut them off, of course, but when you're done with your design, you look at it and you say, well, here's the things I didn't address, but they could be implemented by doing X or Y. For someone with less experience, it's okay for the interview to bring these things up, give you some tips, and then you can just talk about how you would address them. A good example of things to consider for like our web crawler project today would be something like our deduplication service. If we're fetching URLs over and over and we're fetching the same one, we don't want the same URL to have all of its data stored 1,000 times in S3. It's redundant, it's not helpful, and it just costs us money. Another thing might be web crawler traps. This is a bit more advanced, but it shows that you're familiar with what a web crawler is, right? Some sites design circular dependencies in which they are basically a trap for web crawlers to just be stuck in an infinite loop, that they can never leave the page. So how do you defend against these, right? Try to think about all these things once your design is done. Think about how you personally could break this, and then bring that up and talk about how you would defend against these things. All in all, I hope this episode has been helpful in understanding not just how to design a web crawler, but also how the process of designing a system in a systematic way, especially during an interview, feels. I will be following the same structure going forward in new episodes. I'll be including images and things like that. Next episode, we will be diving into designing a URL shortener. A URL shortener is one of the most common problems in system design, so it should be a lot of fun. Again, just another call out. Thank you everyone for your patience while I've been getting these episodes out. It is the holiday season, so if they're like a day or two late, that, could be what's going on. But yeah, I want to give a huge thank you to Devil's Soul on Discord. They had a fantastic question about where they can read transcripts. And if you actually visit the podcast page, learnsystemdesign.buzzsprout.com, click on any of those episodes and you can find a full transcript of the entire episodes. Also, feel free to just email me. Anything I could do to help, I'm always happy to help you guys. I also wanted to give a big thank you to Martin K on the Discord. You had a lot of wonderful feedback. I'll be working on implementing that as much as I can in the future. And finally, I want to give the biggest of thanks to everyone on our Patreon. So a very special thank you to Pranav, Leah Whitelaw, Lucas Anderson, Kalyan Desika, Sergey Bugera, Anil Dugar, Jake Mooney, Charles Gazals, Eduardo Muth Martinez, Wahoo Soares, Adrian Kurek, Gabriel, Jesper Klotzel, Nathaniel Sutton, Florian Breiter, and Clavian S. for being a part of our Patreon and helping and supporting me. If you're listening to this and you've been enjoying the episodes, it would mean a lot to me if you shared this with your colleague or a friend, or just tweet about it. Anything that works. I just appreciate it. I appreciate all of you. You all are my Christmas gift. If you'd like to suggest new topics or even be a guest on the podcast, feel free to drop me an email at learnsystemdesignpod@gmail.com. Remember to include your name if you'd like a shout out. If you'd like to support the podcast, help me pay my bills, please jump over to our Patreon, consider becoming a member. You get the episodes a week early. You also get to vote on the different topics that I'll be covering. All podcasts are inspired by Crystal Rose. All music is written and performed by the wonderful Aimless Orbiter. You can check out more of his music at soundcloud.com/aimlessorbitermusic. And with all that being said, this is Ben, and I'm scaling down.